Okay, thank you very much. It's a great pleasure of mine and a great honor to give a lecture here. It's actually, I have been to Italy only once, and I'm very grateful to the organizers and to Professor Rika, first of all. And I'm going to talk about the families of two groups, G and K and gamma and K. There is a typo here, and their applications in topology, algebra, and geometry. Okay. So here is the book. Actually, the theory of these groups, G and K, was born somewhere in 2015. And since that time, I lectured a lot about those groups. And they naturally appears in the study of braid groups, and actually not only in braid groups, but also in many other areas of topology and algebra and whatever else. And so we are going to introduce these groups. They have fundamental ties with fundamental groups of configuration spaces, whatever configuration spaces. And actually, as we will see, there are lots of relations with law-dimensional topology, group theory, combinatorics, algebra, and geometry. But I really hope that after some discussions, you may ask about whether we can do something in algebraic geometry and maybe in some higher dimensional algebraic topology. So far, it's not quite clear. And this is the book, Invariants and Pictures, which was published in 2020 in World Scientific, series of notes and everything. Actually, after some courses of my lectures were given, this contains a lot of results about these groups G and K. Okay. So, well, I think everyone knows what braid groups are. Actually, we're considering endpoints on the plane. And as usual, we consider a motion of endpoints, so they stay distinct. And we get a path in R3, which can be considered as a loop in the configuration space of n-tuples of points. And they usually connect some fixed points on the top, some fixed n-tuple on the top, and some fixed on the bottom. So this is the braid as we know it everywhere. And actually, braids can be considered as a dynamics of particles. And we will be considering various dynamics of particles, not necessarily points, and correspond some elements of some groups. And actually, here is the fundamental principle, which I formulated in 2015. And this is a principle, this is a motto. And then I will be deciphering this principle step by step by getting some concrete theorems. And I will be considering various concrete properties which lead to homomorphisms of groups to some other groups. Okay, so here is the main principle. If dynamical systems describing some motion of particles possess a nice codimension 1 property governed exactly by k particles, and I would say exactly meaning that not by k minus 1, then these dynamical systems admit a topological invariant valued in groups G and K. The groups will appear on the next slide. And here I just give you a couple of examples just for you to feel what good properties or nice properties can be. For example, if we consider some motion of n particles on the plane, so there can be some property for k equals 3, meaning that some 3 points are collinear. Okay? And for k equals 4, there can be another property that some 4 points belong to the same circle, all line. We will see it. Well, actually, the usual property which gives rise to usual Artin's generators of the braid group is in some sense a GN2 property. So basically, basically the generators we all know for the usual braid groups, so they somehow depend on some property that some two particles share one coordinate. In some sense, it's GN2 properties. You will see what I mean in a minute. Okay. So now what do I mean by good properties? And more or less now I will tell you the recipe how to write down a word, and more or less this will be how to define the homomorphism from the braid group, actually from the pure braid group, to the group GN3. Of course, the group GN3 will need its definition, but more or less, here is the notation, G and K. Maybe you know that there is a very well-known French and Russian notation for choose and K. Actually, for choose and K, we use C and K. C, capital Latin letter C, and N on the bottom and K on the top. So this means choose and K. So these groups G and K mean that we have some group having choose and K generators. Actually, the generators will be indexed by K element subsets of the set of N elements. So maybe from 1 to N. Okay, so actually here we're doing the following. So we have, for example, 4 points, 1, 2, 3, 4. And we have the GN3 property saying that some 3 points are collinear. For example, here, 1, 2, and 3 are collinear. And in this position, I write down the generator A1 to 3. And here, for example, A1, 2, and 4 are collinear. I write down the generator A1 to 4. So actually, I think you understand what I'm doing. So as the time goes, I collect those moments where my good property holds true, and for those moments I write down generators. Of course, I want to require some genericity of the whole dynamics in the sense, for example, that there are exactly finitely many moments of such sort. And for example, that it doesn't happen that for some period of time we have this property holding true, or some transversality condition which are under the reg for a while, but for generic braid, I'm just writing down such a word, okay? And now the definition of the groups G and K comes into play, and actually just from the definition you will see that these groups have to do a lot with many areas of mathematics. Okay, so again, G and K comes from the notation choose and K, and the generators they are indexed by K element subsets of the set from 1 to N, so choose and K in total. And there are 3 types of relations. The first relation says that all generators are reflections. Reflections are involutions, so this makes this group similar to Coxeter groups, and they really have a lot to do with Coxeter groups. The second relation is far commutativity, meaning that if we have 2 sets of indices which are far away from each other, far enough from each other, then they commute. So in some sense, this is very similar to the usual braid group. Maybe for the usual braid group, we should think of generators not just with one index, but better to look at a generator by looking at strands which are involved. Okay, so in braids, we have our usual far commutativity saying that if we have 2 crossings formed by 4 different braids, that they commute. Okay, so usual braids are in some sense GN2 braids, and if we have 2 pairs of indices, they share nothing. And for 3 indices, I allow them to share 1 index. For 4, I will allow to share 2 indices, and so on. So this is a far commutativity relation, which makes the group similar to braids, okay? And tetrahedron relation also known as the Yang-Baxter relation, or higher Yang-Baxter's homological relation, and so on, looks as follows. So assume we have some k+1 tuple of indices, and I take all possible k tuples and order them in whatever way. And then if I order them in the opposite way, then it will be the same. So for example, in the braid group, so we have a sort of Yang-Baxter group-like relation, like Aij, Aik, Ajk equals Ajk, Aik, Aij. So this is the higher version. Okay, and now the theorem, which is just the first witness of the principle I formulated before, any good property, so far good is under the reg, on k particles in R2 induces the homomorphism from the pure braid group to G and K. Okay, well, you may ask me why pure braid group? Well, you see, it's important for me that the generators the particles return to their initial positions, so that if I concatenate two things, I don't rename the indices. So this means that for just braids, it will be a well-defined map, and for pure braids, it will be homomorphism. Well, you may ask me where do these relations come from? Well, actually, the main principle originates from something very easy and very familiar in topology. So when we study some fundamental group of a configuration of a configuration space, we can create some walls. Walls are something of codimension 2, of codimension 1. And we write down a word if we cross the walls. And sometimes some loops in the configuration space are homotopic. But for generators, I need something of codimension 1, and for relators, I need something of codimension 2. So more or less, this means that my codimension 1 property corresponds to generators, and codimension 2 property corresponds to relations. Maybe I can say a couple of words about the most interesting, the third relation here. So for example, if I look at the GN3 representation of the braid group, for GN3 here, I have the following. We can consider some codimension 2 event. Codimension 2 event is as follows. 4 points are collinear. Well, of course, for a typical braid, this doesn't happen. But for a typical homotopy between two braids, it can happen. But I can perturb it a little. And this quadruple will split into 4 triples. So for example, I can have 1, 2, 3, 4 on the same line, and this is not stable, but all triples 1, 2, 4, 1, 2, 3, and so on, they're all stable. And if I perturb them in one direction, I will get what I have on the left-hand side. And in the other direction, I will have the opposite. So that's why this principle works, okay? And actually, we have two concrete situations. One of them is what we have for GN3, 3 points are collinear, and the other GN4, 4 points belong to the same circle, all line, okay? Well, you can ask, do we have other examples? Like this. And actually, I'm very interested in whether we can look at tropical GNK theory. So when we look at some polynomials or when we replace some properties, some algebraic expressions with tropical algebraic expressions, or maybe if we replace our usual lines with tropical lines and so on. And actually, here I may say that we can also run the GN2 theory by using the following formula. Some 2 points share the same x coordinate. So this more or less corresponds to usual Artin generators. Okay. So now I want to tell you some situation where the ideology fails. So the principle which is not good, okay? For example, we can consider a motion of points, the dynamics in the free space. And so here is a codimension one property. Some 4 points are coplanar, okay? And somehow this should give us some presentation of the braid group for R3. But we know that in R3, the fundamental group of configuration spaces is trivial. So there will be not a natural braid group here, okay? So a priori, everything will be trivial, right? And actually, a posteriori, we can say the following. Well, you see, if some 3 points are collinear, then whatever 4th point we add, these 4 will be coplanar. So this means that the property 4 points are coplanar is governed not quite by 4 points, but in some cases it may be caught by 3 points. And that's bad. That's where the ideology fails. So a posteriori, GN4 doesn't work here, but it does work if we correct our configuration space. Namely, we can consider configurations of n points, maybe n should be small n, not capital N, in R3 with not 3 points collinear. And in this case, GN4 works well. So we will have a homomorphism from this configuration space to GN4. Well, and actually the reason is quite understandable. Well, so if we consider collections of points in R3, the fundamental group will be trivial. But here we cut away something of codimension 2, which makes a non-trivial fundamental group. Well, and actually, in some sense, we can say that the number of points, all points are generic until the number of points is as much as we need. I mean, for points in R3, we require that any 3 are generic, and only 4 of them can be non-generic, and this will give me GN4. And you see, in some sense, for points on the plane, it's also like that, because if we consider whatever points on the plane, and we don't make restriction that any 2 of them are distinct, then it will be a trivial configuration space, right? And so if we make some distinction that any 2 points are generic, then it goes well, okay? And similarly, we can do the same for RK-1, and actually for RPK-1, it works just verbally, okay? Well, do groups G and K work in the situation when particles are not points? Well, yes, they do, and there are lots of examples. There is a whole book. And actually, the first thing we can start from is we can use the projective duality. So assume we live in RPK, okay? And we can use hypersurfaces instead of points. And for example, we have lots of dual theorems. So instead of saying that some 3 points are collinear, we can say that some 3 lines pass through the same point if we are in 2-dimensional space, right? And the same for higher dimensions. And actually, you can say, okay, this is just a reformulation, and we already knew that. Well, but we can do the same for pseudolines, or we can do something for curves. So the only property of lines we need here actually is that any 2 lines intersect at exactly 1 point, more or less. So actually, we can consider lots of interesting moduli spaces and maybe infinite dimensional, satisfying some genericity conditions, and the fundamental groups of these configuration spaces will give rise to will be mapped to corresponding G and Ks. Okay, and actually, I think not so much is calculated here, so I encourage students and other people to calculate such configuration spaces. And actually, one can even study manifolds by looking at the GNK theory. So, you know, in his first paper about link homotopy, Milner says, okay, so here, for example, we have different manifolds which have the same homotopy type, but they're really different because link homotopy theory in them is different. But we can say, okay, but maybe we can look at dynamics of hypersurfaces or dynamics of points or dynamics of whatever else. And if we have a topological space, we can organize some dynamics, and maybe topological spaces with different dynamics will give rise to different subgroups and GNK and so on. Something was initiated in the book I showed on the first pages, but still there is a lot of work to do. Okay, well, and actually now I want to pass to something which is not quite good, and some motivation example which led me to the which led me to the definition of gamma NK. Well, in fact, sometimes GNK doesn't work quite well. What do I mean? Well, you see, I can look at dynamics on points on two-dimensional surfaces, even on the torus. Well, what properties did I take on the plane? Well, you know, one thing I took was 3 points are collinear. You see, instead of lines, I can say, okay, maybe 3 points are in the same geodesics. And here are two things. One of them is bad, and the second is fatal. The bad thing is that through any 2 points, there are many geodesics, not just one. And for example, if I have 1, 2, and 3, or one geodesic, but some 1, 2, and 4 are on the other geodesic, so these two events are somehow independent. And since they are independent, the corresponding generator should commute, and this will spoil the whole structure, because there is no commutativity relation between 1 to 4 and 1 to 3. By the way, the commutativity relation between, say, 1 to 3 and 1 to 5, this relation is written in the definition of GN3, because the property that 1, 2, 3 are collinear and 1, 4, 5 are collinear, these two things are independent. So they they should commute. But here you see one relation is spoiled. But this is not the worst thing I can say. And the worst thing is that there are infinitely many geodesics. And if we try to write the generators on a sheet of paper, we will have to write infinitely many letters in an infinitely small segment. So this spoils the situation completely. And this was one of motivations why I introduced the groups gamma. By the way, here I have to give credit to many of my co-authors. So first of all, I have to give credit to my co-authors of the book, Igor Mikhailovich Nikonov and Denis Alexandrovich Fedoseev and Kim Song-John. Well, and also there are many other people I may mention, and all those who was working on these groups and shared our interest to that. Well, actually, now I want to pass to Delaunay triangulation. So since it's not just only a conference, but a summer school, I can say some words about what Delaunay triangulations are. Actually, it is very interesting that any manifolds with metrics can be given triangulations. So assume we have points on a manifold. Then we can make a tie link between these points as follows. So we can draw a world map on this manifold as follows. So by looking at a point, we can look at all those points which are closer to this one than to any other. So we have this inequality, and actually this makes a tiling of space. Well, if metric is good enough, because if it's not good enough, there can be some unpleasant thing may happen. But normally this is called the Voronoi tiling. And dynamics of points induce dynamics of Delaunay triangulation. The Delaunay triangulation is something which is or maybe Delaunay simplicial is something which is dual to the Voronoi tiling. Actually, we can say that our points are in the capitals of the neighboring of the countries, and our boundaries of the borders between countries are those points when we have an equality. So the distance from one capital is equal to the distance from the other capital. And the dual thing is when we connect capitals of adjacent countries. So generically, for a two surface, this will give a triangulation. But non-generically, it may happen that four countries have a common point on the boundary. Okay, so generically we will have a triangulation, and I will work mostly with two-dimensional case, and actually I will mostly work with groups which will be called GN4 because it will give rise to some relations which deal with 4 indices. However, similar things can be done for higher dimensional spaces, and a lot is written in the book and in some other articles. Well, okay, and again, I will start mostly with the example concerning braid groups. I will introduce gamma and k. And for the braid groups, I will give an exact description of this map. And after that, we will see that it has a lot to do with cluster algebras and whatever else areas of mathematics. So let's welcome the groups gamma and 4. Well, actually, so first of all, these groups are indexed by quadruples of indices from 1 to n, but unlike GN4, here the indices are partially ordered. Namely, I don't quite require the ordering, but what I require is that I indicate which two indices are opposite. So actually, for 4 indices, there are 3 possibilities to say. 1 is opposite to 3, or to 4, or to 2. And actually, the relation 4 here says nothing but the fact that from all 24 permutations, there are 3 classes of generators. And actually, the total number of generators will be 3 times as much as in GN4. Okay? The first group of relation is the same, so that all generators squared equal 1. The second, again, is the same, so if they share no more than 2 indices, it's 1. But the third relation is something more interesting. So in GN4, the relation has length 10. So we have some 5. Some product of 5, which is equal to some other to the opposite product of 5. But here the length is exactly 5, and I will tell you what's going on here. Okay? Actually, what do generators usually correspond to? Well, they correspond to some codimension 1 events. And in our situation, we deal with triangulations. A triangulation changes its combinatorial type when we undergo a flip. What does it mean we have a flip? It means that some 4 neighboring points, not any points, but neighboring, are on the same circle. Neighboring meaning that no other point lives inside the circle. Because if we have some point inside the circle, then somehow these points do not share a common border, not share a common boundary. Okay, and what do these relations mean, 2 and 3? 2 means that independent flips commute. Well, it's typical. And as for the third relation, it's the most interesting thing is the following. Well, we can consider possible triangulations of pentagon. There are 5 of them. Well, I mean without additional points. And we can make flip here. We can make a flip again. And after 5 flips, we return to the initial position. You see? Well, you can ask me why length 5, not length 10, as in GN4. The reason is that in GN4, we are interested in all situations when 4 points are on the same circle. But here, we're interested whether the 5th point is outside the circle. So any second generator is taken away. Okay, and you see now we have something to do with the space of triangulation of a polygon, and actually this is a very popular direction in science. So this has to do with cluster algebras and many other things, with Stashev polytopes, and it looks like people who studied spaces of triangulations. They studied it combinatorially. They studied it topologically. They studied it from many other points of view, but it seems that many people just overlooked the group structures of groups acting on these spaces. So, for example, we have 2 triangulation of the quadrilateral. We have 5 triangulation of the pentagon, which means that for quadrilateral we have a segment. For the pentagon we have a pentagon, and for the hexagon we will have the associahedron. But I saw no instance of the group. So in some sense, gamma and k are the groups which naturally correspond to these things. And actually now cluster out. So here is the Stashev polytope associahedron, which corresponds to triangulations of the hexagon. So there are, I think, 14 of them. And actually now one thing which means that Ptolemy yields pentagon. Maybe I didn't say it I didn't write it in slides, but I will say it verbally. That there is a well-defined map from the braid group on the plane to gamma and 4. Well, the recipe is very easy, so we just look at triangulations, and whenever we have a flip, we write down AIJKL as IJKL are on the same circle and I and K are opposite. Well, the proof of that this is well defined is just the same for G and K. For gamma and for G, the proof is the same because generators are codimension 1 and relators are codimension 2. Okay, so there are maps from braids to gammas. Okay. And actually now I want to say something about invariants of braids, which makes the whole science to be very much related to cluster algebras and some other things. Now I just say about something very popular in cluster algebras, which means Ptolemy yields pentagon. Well, there is a very nice Ptolemy theorem, which is known from school, that if we have an inscribed quadrilateral, then the sum of products of opposite sides equals the product of diagonal. So we may see that if there is a flip, yeah, by the way, when I was talking about braids, right? So you see the braid, if I have 5 points which are near to be on the same circle, almost on the same circle, and I make some small movements of such points, then the braid will be definitely trivial because there is no way of for one point to go around the other one. So this braid has to be presumably trivial. And Ptolemy yields pentagon means the following. So assume we have a triangulation, and we associate variables to edges of the triangulation. And the idea is that whenever we undergo a flip for a quadrilateral and we exchange one diagonal with the other one will be just the product AC plus BD over X, meaning that we use this formula. And then some miracle appears, and this miracle is very well known for cluster algebras. The theorem is as follows. So if we do 5 flips and return to the initial position, then when we perform all those transformations like AC plus BD over X, we will return to the initial variables. Okay. Moreover, some other features happen here. Very nice features. For example, that all intermediate labels will be just Laurent polynomials. It's impossible to have x plus 1 in the denominator. Okay. Also, everything in the denominator will be positive. All coefficients are positive. And actually, there are no minus signs and proofs. And you see, since there are no signs, minus signs and proofs, this means that we can do the tropical version. Well, you see, if we have some theorem about addition and multiplication when we use distributivity, but for addition we don't use subtraction at all, then we can pass from fields to semi-fields. I mean, for example, instead of saying A times B, I can say A plus B, and instead of saying A plus B, I can say A maximum of A and B. And for example, here, I can use another formula and write Z equals maximum of C plus E minus Y and X plus D minus Y, something like that. And the theory will perfectly work. Well, now Ptolemy yields pentagon. Here is the proof. Actually, here is the proof just on one slide. So I have these 5 edges and these 2 diagonals. I perform one flip. This is Z. Okay, this is Z instead of Y. I use another flip. Here is T instead of X. Here are all the formulas. So I have T, and then I use use V instead of U. And there will be a miracle that here here I will get something equal to Y, and here I will have something equal to X. I will return to the initial Y and X. And this is actually the proof of the fact that this Ptolemy gives me a presentation of the braid group, right? Okay, and similar things can be done for braids, for arbitrary 2 surfaces, and actually one can play lots of games here. Actually, well, if we have sufficiently many points on a surface to give rise to triangulations, then we can move these points, and triangulations can be considered in different metrics. So, for example, I can use metrics which are defined geometrically, and for example, I can consider a torus 10 times 10 or a torus 1 times 100, and there will be different dynamics of points. There will be different presentation, Delaunay triangulations, different braid group presentations to gamma, and there are lots of things to do here actually. And this, of course, as I said, that this map gives rise to a homomorphism from pure braid groups to gamma n for, well, of course, pure braids, because otherwise it will be not a homomorphism, but just a well-defined map. Of course, the main principle is that generators are something of codimension 1 and relators are something of codimension 2. Okay, well, and now I want to say something about unsolved problems. And actually, there are lots of, well, I think each of these points can give rise to a whole theory. But actually, well, in some sense, I'm very puzzled that these braid invariants are very hard to do work with not invariants. Actually, something like stabilization or Markov moves are very it's hard to do Markov moves for G and K, very hard, even for G and 3, because adding a new strand gives lots of new generators, not just one generator, and it's hard to handle. As for gamma, well, there is some problem concerning division by 0. I can talk personally about that. Well, actually, there is one question about G and K hierarchies. Well, you see, the G and 2 properties for points on the plane, well, is as follows. 2 points share the same x coordinate, right? 3 points are on the plane. This means that 3 points are collinear. 4 points belong to the same circle. What next? Maybe 6 points belonging to a conic. Well, not quite, because there are some degenerate conics, and one has to resolve singularities, and this can give rise to yet another theory. Well, also the generalized to algebraic geometry, or maybe to complex geometry, or maybe whatever geometry with whatever top structures. You see, so far I was looking for some properties which are quite easy. I mean, 3 points are collinear, but this deals with just some metrics on the Euclidean space. For example, we can do some gamma on the torus, but what if we look at the torus as some not as a torus, but as an elliptic curve? Well, maybe then we can use some additional law or something else. Maybe if we have a surface with a complex structure, we can use this complex structure. So you see, for G and K and for gamma and K, there are some principles, so that if we just fit into this principle, we will again get invariance of the structure. So I want to make this principles to feel the algebraic structure, the complex structures, and so on. Well, non-integrable structures. What do I mean by non-integrable? Well, you see, in some sense, all structures for points, all K properties for points I formulated so far look like that. All points belong to some prefixed curve, right? So, for example, all 3 points belong to a line, and there is a set of lines which is fixed once forever, and we make 3 points which belong to a line. But maybe there are some properties which are not static, so the family of curves may change. Or maybe the G and K property may not be the property that we belong to some family, maybe something else. Well, homotopy groups of spheres, well, maybe yeah, I'm not going to say much about that, but braids and Brownian braids Brownian braids can be studied by using G and K. Well, smooth structures and whatever other geometric structures, complex structures, whatever they can give rise to some properties. So maybe for one smooth structure there will be one gamma presentation, and for the other there can be another representation. Tropical, well, maybe I said something about. Well, I think I said something about tropical gamma presentation for braid groups. We will have tropical Laurent polynomials, and it's a good project for students, I think. And actually, I don't know how to use it for enumerative algebraic geometry. And maybe some word about algebraic geometry. Just let's return to these 3 properties again. 2 points have the same x coordinate, G and 2. So this means that some real part of Zi minus J equals 0, right? And 3 points are collinear. So this can be rewritten as some imaginary part. Well, never mind, real or imaginary equals 0. Okay. And 4 points. Oh, no, a typo, integer. No, of course. 4 points have real cross ratio, a real cross ratio. So if 4 points on the complex plane, are on the same line or on the same circles, then their cross ratio is real. Okay. And now I'm very interested in the following way. Maybe this is not just a specific phenomenon for some polynomials, but maybe there is a whole family of such polynomials. What do I mean? Well, everything here. So, for example, we can say that we have one complex coordinate, which is two real coordinates. Everything here can be described as polynomials or maybe as rational functions. So, okay, and now I have a very interesting feature. For example, if I have, say, 3 points, 1 to 3, which are collinear, and 1 to 4, which are collinear, then I don't know, 1, 3, 4 and 2, 3, 4 will be collinear again. So if so we have an interesting function, so that if it is 0 for 1 to 3 and if it is 0 for 1 to 4, then it will be 0 for two other triples. And the same for quadruples when I mean cross ratio. Maybe this is a phenomenon that algebraic geometers know better. I don't know, but this potentially can give rise to some other GNK or gamma NK structures on not only on manifolds but on algebraic varieties, because algebraic varieties may have lots of other properties. Say, instead of torus, we can consider an elliptic curve. Well, I think this is the right time for me to stop here. Okay, thank you very much for